All right, chapter 2, matter and energy. What is matter? Matter is defined as anything that occupies space and has mass, which is most things. Not everything, but lots of things are matter. We are matter because we occupy space and we have mass. You occupy space, you have mass, you matter. We're missing the R there, but it's fun. Lots of types of matter are easily visible. Chairs, tables, humans. Often easy to see. Other types of matter are impossible to see without magnification, like the particles that make up the air, other small things like bacteria, usually hard to see without magnification. They still take up space, they still have mass, so they qualify as matter. Matter often looks smooth and continuous, like in the case of our desktops or the surface of the whiteboard. It feels continuous and smooth, but if you zoom in far enough, you will find out that it's not actually smooth and continuous. All matter is composed of atoms. Atoms are really, really small, so if you take an average human hair, they're about 100,000 times thinner than a human hair. So if you take a hair and you were to stack up atoms one after the other, you'd have 100,000 to get the width of the hair. So that's the sort of like how small we're talking about. These are the fundamental building blocks of matter. So these are the smallest little Lego piece that builds our world. You can also get these pieces to join together, like Lego bricks, Lego bricks, to form molecules. Molecules are two or more atoms joined together. Atom is a single piece. A molecule, multiple atoms put together. We'll add of matter there for atoms. Everything that's matter is ultimately composed of atoms when you get down to a close enough zoomed in look. Sometimes they exist as independent particles, so they're just kind of sitting next to each other. In metals, this is typically the case. You can think of them as just like orbs or balls just kind of sitting next to each other, like in a ball pit, sort of. In other things, they are bonded together in well-defined structures. So these colored orbs, balls, represent atoms, and then the lines in between them that are gray are the bonds. And so this is a particular molecule. I forget which one it is. It might be caffeine. That would have been something I might have chosen. It's probably not. So that's sort of what an atom, atoms look like here, and molecules, we just combined a couple of them together. And now we'll take a quick side tour to talk about states of matter. Hopefully, we're somewhat familiar with our states of matter. We've got 3 that we're going to care about for this class: solid, liquid, gas. These are the common states of matter. And we're going to learn some characteristics of solid, liquid, and gas. Starting up with our solid state. In the solid state, atoms and molecules, whichever we're made up of, are packed close together and in fixed locations. I often refer to this as touchingly close. They're close enough to each other that they interact. So they're touchingly close, and they have fixed positions. Although they're locked into their position, they're still moving around. They're wiggling, they're jiggling. There's names for the different ways that like molecules wiggle and jiggle. We're not going to learn those, but there are fun names for those. So they may vibrate or oscillate, but they're not moving around each other. So solids have a fixed volume and a rigid shape. Fixed volume because they're touchingly close. There's not empty space. You can't compress them any closer together. and a rigid shape because they're fixed in their positions. They're locked in relative to their neighbors. Solid state is sort of like how we're all arranged in the classroom. Each of us, for the most part, is kind of locked into our own seat. You're close enough that you can interact with your neighbors. There's not like tons and tons of empty seats. And you're also able to move around and do your own thing. Also similar to kind of being at a movie theater. So this is like sitting in lecture or at a movie theater. The people at a movie theater. At a movie people. Great. We'll do ER today. The solid state, there's two types of solid states that we can have. One of them is crystalline solids. Crystalline means that it has long-range repeating order. Basically, it forms crystals. So if you were to zoom in the microscopic level, we've got crystal structure up here on the top right for quartz. You can see how this has a repeating structure to it. So if we were to pan over with this zoomed in image, if we were to scooch over to the left and take a snapshot there, we would be able to get those two images to overlap each other. We might have to, finagle it a little bit, move them around a bit, but we would be able to get them to overlap because of that long-range repeating order. The other option is amorphous solids, which do not have long-range repeating order. And an example of that is silicon dioxide glass, like glass, one of the types of glass. And you can see that this structure, this image, if we were to pan over to a different part of it, imagining that it's all kind of random, it would be very hard to find another spot where we'd be able to get it to overlay because it's not repeating the same pattern over and over and over again. So things that have crystalline structure, things like quartz and other gems, some metals form crystalline solids. Amorphous would be things like most glasses, even though they're made of the same thing as quartz. Moving on to our liquid state. In our liquid state, the atoms and the molecules are still touchingly close. They're close enough that they're constantly interacting with their neighbors. There's no empty space between them. However, they're free to move around and past each other. So they're free to move past, we'll call them neighbors. So liquids have a fixed volume because of being touchingly close, but because they're free to move past their neighbors, you can have the molecules or the atoms constantly cascading past and over each other, and that's what allows liquids to flow, because they're free to move relative to one another. And this is kind of like people at a concert. I'm especially thinking of the people that would be pressed up to the front of the concert, assuming that we're not like at the symphony or something, because that would be weird. So we're pressed up to the front. We're at a Megan Thee Stallion concert. All the people pressed up in the front. There's no extra space. There's basically no extra space between the people all the way packed up in the front. However, they can still move past each other. So if you've got a friend and you're like, hey, I want to turn at the front for this song. This one's a banger. You could swap places. You got front last time. If you needed to, you could work your way out of the crowd, go use the restroom, and then try to work your way back into the crowd. Good luck. But you can move past each other. You can interact, but you're still touchingly close. You can't squeeze those people any closer together without crimes occurring. So that's the liquid state. The gas state is not touchingly close. So in the gas state, now we've got empty space between our particles, between our atoms, between our molecules. whatever they're made of. And because they're completely separated from their neighbors, they can, move independently of them as well. Because of the empty space between the particles, gases are compressible. You can push them closer together, and it just reduces the amount of empty space that they have. So for example, if we take all of these red dots and we push down on this lid, we can compress the same number of red dots into a smaller space. They're not touching. We still have empty space in there, so it's still a gas, but they're closer together. We've compressed the space. And this is why you can do that fun trick with like the $1 plastic water bottles where you squeeze the bottom and then it builds up a bunch of pressure and then you quickly flick the top off and then the cap flies into the air. That's taking advantage of the compressible nature of gases. So the gas state sort of like happens when we leave lecture. Once we're done with lecture, you all pile into a liquid state as you're trying to exit the class, and then you all separate and go your own ways and do whatever you want after that. So this is like after lecture or potentially in lab. We're moving around doing whatever we want. So the compressibility is an important point for the gas state. Another thing that I want to note for the liquid state, hydraulic presses use liquids because they're touchingly close. You can't compress the liquid at all very much, but because they can move past their neighbors, the molecules can move past their neighbors, you can take a really large surface area and push down a little bit and then funnel all that pressure into a small area, and it like super jacks up the pressure on that one little area, and that's how hydraulic presses work. That's just for fun. I just think that's cool. I looked it up and I was like, oh, that makes sense. That actually makes so much sense. I should have thought of that. Okay, and then this is a table that has some of the characteristics like the shape, the volume, intermolecular interaction strength, which we'll talk about way further in the future, and the relative particle position. So in solids, we have definite shape, definite volume. That's why my Apple Pencil doesn't melt. It doesn't. I don't have to worry about it turning into goop and flowing onto the floor if I set it down. The particle positions, they're in contact, they're touchingly close, and they're also locked into their positions. They're not moving relative to their neighbors. For our liquids, they have indefinite shape, but definite volume. So you can't compress them, you can't make them fit into a smaller space, but they'll take the shape of their container. They are in contact with their neighbors, the particles, they're touchingly close, but they're not fixed. They can move past their neighbors. And then in gases, they're indefinite shape and indefinite volume. You can compress them, and they'll take up the shape of whatever the room is, and they're not in contact. They're just kind of randomly dispersed. Any questions about our states of matter? All right, another way that we can classify matter is by a pure substance or a mixture. So a pure substance, only one thing. A mixture, two or more things, two or more types of substances. It can either be atoms or molecules. You can have different proportions of how you've got them mixed together. So everything is either a pure substance, it's only one thing, or it's a mixture. It's two or more things and they're combined together, two or more types of atoms or molecules. Underneath each of those, pure substance and the mixture, we've also got subcategories. So here's like a sort of a choose your own adventure chart. Starting with all matter, you can determine if it's a pure substance or a mixture. From each of these, you can figure out if it's one of these four subheaders, and we'll talk about those subcategories: element, compound, homogeneous, heterogeneous. There's also examples there. So this might be a helpful reference slide for later. All right, so for our pure substances, one of our types of pure substances is elements. Elements cannot be transformed or decomposed into simpler substances. All of our elements, all 118 of them, are found on the periodic table. So if it shows up on the periodic table, the one we have in class, or the one that's on your yellow sheet, if it shows up there, if it has a box, it's an element. One type of pure substance is elements. Another type of pure substance is compounds. Compounds, 2 or more elements combined with definite proportions, like a specific recipe of mixing together several elements. It has to be the same definite proportions for it to be that one compound, which we'll talk about later. Compounds are much more common than elements. If you look at all 118 options that we have on our periodic table, most of them are inaccessible to us. But you can probably think of lots and lots of ways that you can combine 118 things, even if it's just one of one and one of another. But you can have like multiple. So there's like limitless possibilities for how you can combine different elements. Compounds can be decomposed into simpler substances. So you can break them down, hit them with a big hammer, and break them down into their elements. So break the bonds that bind them together to turn them back into their elements. And then separately, we've got mixtures. So we were talking about pure substances, we have elements, anything that's on our periodic table. We've got compounds, 2 or more things on our periodic table. And then we also have mixtures. Mixtures are substances that are just mixed together, not chemically combined. So if you have a bag, if you have a purse, if you look inside of it, that's a mixture of all the things that you decided you wanted to carry with you today or things you forgot that you had. That's a mixture. They're not chemically combined. They're not like stuck to each other, hopefully, not stuck to each other. It's just a bunch of separate things kind of all in the same spot. You could separate it out. You can go through and sort your bag, your purse, your satchel. You can have different proportions. One day you might decide, I need 5 phones. I'm going to put 5 phones in my bag. Other days, maybe it's a 1 phone day, you know? So you're going to take some of those phones out. You can have different proportions. A couple types of mixtures, examples of mixtures, like salt mixed into water or sand mixed into water. Those are 2 different types of mixtures we'll talk about here. So our mixtures can be classified by how uniformly or smoothly or evenly they mix. Homogeneous mixture has the same composition throughout. Smooth, consistent composition. Texture. Examples, things like lemonade. Hopefully your lemonade, if you take a sip from the bottom of your lemonade, you get a taste for that. You take a sip from the top of your lemonade, you get a taste for that. It should be the same taste. Pepsi, Coca-Cola, Dr. Pepper, Mountain Dew Baja Blast, the nectar of the gods. Right, all of these things, if you take a sip from one part of a container and the other part of the container, any 2 places that you sample should be the same flavor, should be the same mixture, the same ratio of all the different flavors and compounds and things. That's a homogeneous mixture, smooth, even consistency throughout. A heterogeneous mixture has different composition throughout. Different ratio or composition throughout. So like trail mix. If you have a big bowl of trail mix, you take a small handful, you eat your trail mix. Ooh, I got a lot of raisins on that one. What a treat. It's probably not what most of us are thinking, but you know, oh, a lot of raisins, really nice. You take another handful. Ooh, that one was all peanuts. Nuts. You take another handful. Ooh, it's all M&Ms for some reason, right? You're going to get a different experience every single time that you take from that. It's got a different consistency throughout. So things like stones like marble, chicken noodle soup, hopefully, has a different consistency throughout. Sometimes you get a lot of noodles, sometimes you get a lot of chicken. If you're getting the same smooth consistency throughout your chicken noodle soup, get help. Don't blend your chicken noodle soup. Vinaigrette salad dressing is also a good example, or like mustard, things that when they sit in the fridge long enough, you have to shake them up again before you use them. If you don't shake them up before you use them, you're getting the like weird mustard juice, you know, on your burger or your hot dog or your bean burger, whatever you eat. Okay, so those are examples of heterogeneous, homogeneous. Let's identify each of these substances as either a compound, an element, a heterogeneous mixture, or a homogeneous mixture. We've got, first up, a stuffed animal shark. A stuffed animal that's in the shape of a shark. Is that going to be a compound or an element? No. It's going to be a mixture. Is it going to be a heterogeneous mixture or a homogeneous mixture? If we take a bite out of it, at the head, bite out of the tail, are we going to get the same ratio of all the components of our shark? Probably not. If we take a bite out of the head, maybe we get the little eye piece, really chewy, don't like it. We take a bite out of the tail, probably, hopefully, just all, you know, a little bit of fluff, but a lot of like the skin covering fabric. I don't know, that's the weirdest way that I've described that so far. It's not the same thing everywhere that you cut it. This would be a heterogeneous mixture. We also have coffee, beautiful, wonderful coffee. Is coffee a pure substance or a mixture? It is a mixture. Is it a homogeneous mixture or a heterogeneous mixture? Homogeneous mixture. It should be the same consistency throughout. If it's, I believe it's called cowboy coffee, where you just put the grounds in the hot water and then you drink it and sieve it through your teeth, that would be heterogeneous. But we don't drink cowboy coffee because we're not cowboys. All right, C, alcohol in the thermometer, which is what most like liquid thermometers have. The alcohol part specifically of the thermometer. Is that going to be a compound, an element, a heterogeneous mixture, or a homogeneous mixture? Yeah, it's going to be a compound. Really, it's probably not a compound. It's probably a homogeneous mixture because they add some like color to it. But the alcohol just by itself would be a compound. It's a bunch of elements combined together. How about selenium? Selenium is an element. It's Se, symbol Se, on our periodic table. So this is an element. It's got its own box. Questions about any of these classifications of matter examples? Yes?
Just to clarify, for the mixture one, the salt water would be considered homogeneous and the sand would be heterogeneous?
Yeah, so going back to these visuals, the salt water, assuming the salt is dissolved in the water, this is going to be homogeneous, same consistency throughout. The sand in the water is going to be heterogeneous. It's a different consistency throughout. All right, quick summary. Matter can be either a pure substance or a mixture. We saw that flow chart earlier. If it's a pure substance, it can either be an element, shows up on our periodic table, or it's a bunch of them put together, a compound. Our mixtures can either be homogeneous, nice smooth consistency throughout, or heterogeneous. And mixtures can be made up of any two things. It can be two or more elements, two or more compounds, or a combination of both elements and compounds. And we will pick up with physical and chemical properties next time.